Vient d'Afrique du Sud. Il est donc à l'université de Stellenbosch dans la région de Cape Town. Et il a commencé sa carrière comme ingénieur géotechnicien. D'ailleurs, vous verrez, il va effectivement nous parler de recyclage en place à froid, mais avec des cercles de mort et donc avec des lois de Coulomb, je ne sais pas, peut-être. En tout cas, on partage ça ensemble, puisque j'ai commencé aussi comme ingénieur géotechnicien. Donc, Kim, the floor is yours.
Merci beaucoup, Monsieur Président. Pardon, je n'ai possible parler pas français, but I can continue with a French accent if you like. But I don't believe it's sustainable. So you're going to have to hear my South African accent. Thank you for the introduction. Also, thank you for PPRS for this invitation. It is so encouraging to see the developments in these efficient technologies in terms of energy and emissions and other very important issues. And I would like to join in explaining some developments. Okay, sorry, that's just where I come from. We are low on water, but we're hoping the rains will come. I have a four-part presentation where I would like to talk about, in particular, some of the problem solving, and as you can see, it's the typical loop solution to problem solving. And with cold recycling, as we've heard from a previous speaker, there's some needs and challenges, particularly in mixed design and pavement design as this technology matures. So I'd like to take you through this loop. So we know that we need to be aware of what the problems are. We need to acquire information and knowledge in those areas, then develop the tools and implement. But I think an area that all over we commonly fail is in closing this loop and refining the technology. So we're aware of the types of failure mechanisms. We know how to gather the information and acquire the knowledge and develop the tools, and I'll share a little bit about that with you. But then we implement, and that's generally where we stop. And we are faced with criticism by people who don't enjoy our roads. So we need to close this loop, do a reality check of this implemented technology and how it performs over time. And this is not like that sign that says free beer tomorrow, and if you don't close the loop, you go back again tomorrow and the sign still says free beer tomorrow. So we need to close this loop. So in the first step, just awareness of the challenges we're facing. And I'd like to emphasize these numbers are conceptual. We know that globally there's in the order of 65 million kilometers of roads, of which about 18 to 20 million kilometers are surfaced globally. And really, I'd like to just emphasize that there is such an important need for recycling and maintenance technology, because if we work on a design life of a road of 18 years, we're talking about 1 million kilometers in the world coming up for structural rehabilitation every year. And are we keeping up with that? I think this is a big challenge we've got to ask ourselves in all the different countries. And then on top of that, how do we recycle these materials? And particularly with a focus on recycling asphalt, we could easily be generating about 500 million cubic meters of RAP per year. And how we use that RAP questions sustainability. There's a place for all technologies, as our first speaker explained, in this graph two-dimensionally that explains the influence of aggregate temperature requirement on the horizontal axis on the consumption of energy. Yes, there's a place for hot mix asphalt. We've seen in the previous presentation, the benefits of going the warm route and saving some energy. But there's nothing like working a bit further down that energy loop where you're not having to vaporize the moisture and work in these lower temperature zones. And a lot of researchers have shown 50% savings in energy as you move to the left of those temperatures, and in excess of 70% savings in emissions. So the question is, how do we optimize this cold technology zone on the left? I've borrowed this figure out of very good work that was done by Colas some years ago, and I'm not going to go into all the details. I think many of you have seen this data, but it does emphasize when one goes into the cold technologies shown over here, one can have a look at the aggregated energy consumption, just as one example, to show the benefits of reducing temperature in using these technologies. Another question arises, this is part of the awareness, of when we're dealing with this RAP, the developed world is using between 15 and up to 100% back into hot mix or warm mix technology. In the developing world, a much lower percentage is used. And we need to look carefully at how that RAP has been implemented and where does it go. In the second part of the loop, the second step, acquiring the knowledge, we heard previously, and I'm just emphasizing that again, is that if we're using cold recycling and we want to create flexible pavements that are less likely to crack and well-balanced pavements where bitumen stabilized materials are supporting the more strongly bound asphalt layers on top, we have emulsion and foam technology, and as we heard from the NCHRP study, the performance that's generated by these two technologies is very comparable. So it comes down to the specific aggregates one's working with and the climate and other considerations in terms of the decision making. In addition, if we look at where these so-called bitumen stabilized materials fit in a two-dimensional matrix, where we've got bitumen on the horizontal scale and the active filler, cement or lime, on the vertical scale, we know that as we move upward, we get stronger materials, but more strongly bound and rigid materials. As we move horizontally, we get more flexible materials, but more expensive materials. And this bitumen stabilized material, where the focus has been, and I don't say it's the only way it can be implemented, but we're talking about half of the added bitumen content to these mixes with a restriction on the active filler to keep these mixes flexible. And there's some sort of an imaginary boundary between your primary distress mechanism and damage factor being rutting below this imaginary line versus cracking and fatigue above that. Yes, one can push more cement and more lime into the material to take you across this line, but then you're dealing with a different type of performing base material. We've also learned over time that what makes bitumen stabilized materials, whether foam or emulsion as binder, challenging is this resilient modulus, because over time we, from many studies, have seen that there's initially an increase in the stiffness as this material cures and loses some of the moisture. This is a cold mix. And then plateaus, but then will obviously suffer some damage over time. And this is an example of a study over 4 years. In the background, you can see a highway in Greece that was treated in 2002, 2003. And we're still gathering data on that particular pavement, still performing very well. And then in terms of the technology, we've seen machines that can control the layer thickness very accurately, because here we're talking about a significant structural layer, which is one of our major challenges as well. In the world, and it was spoken about at one of the earlier sessions, this grey debt where the electoral cycle pushes on the structural investment in our pavements and just treats the top. We've got to do something about these pavements structurally because it's not economical otherwise. So we need to get those layer thicknesses accurate. In developing the tools from the data that we've gathered, I'd like to share something that's come through many years of research, 2 decades at least, and in various parts of the globe. But we've recognized working with these bitumen stabilized materials. We started with, first of all, Marshall compaction, and then we went across to modified Proctor compaction. And we realized, no, we need to be simulating more closely the compaction that happens in the field, which is with vibrating rollers. So a system was tested out, we researched this, and has been independently implemented as a commercially available system using a vibrating hammer with similar amplitudes and frequencies as the vibrating rollers and simulating a much closer packing in this material. And in the subject area we share, which is the geotechnical background, we've also recognized the importance of how we test these materials. Hopefully that 2-dimensional matrix showed you that BSM is not granular, although it has some granular characteristics, and it's not asphalt, it's not continuously bound. So it needs its proper evaluation tools, and what we found is triaxial testing is a very reliable way of testing the performance of these materials. So we've developed a simple triaxial testing system, and it honestly isn't any more difficult than doing an RTS test. It takes some more material, but the process is working very nicely. So what do we get out of this? Well, we get more Coulomb circles and more circles and more circles. As you'll see, we do a lot of more Coulomb plots. And what do we see from these tests? And typically now in mixed designs, we are using these tests. So they're for decision making. This is not just in the realms of research. At 4 different confinement stresses, as you can see, 0, 50, 100, 200 kPa. And we'll do 2 repeat tests. So you use 8 specimens to get your cohesion and friction angle, your 2 primary shear parameters. And what one sees from a granular to a bitumen stabilized material is because they're non-continuously bound, you still retain the friction. It's unlike asphalt. You haven't got a film of bitumen separating the materials. Here you've got, if I can say, flexible spot welds of bitumen. However, the added benefit of this flexible bitumen is giving you a kick in the cohesion. So it's pushing up your shear failure envelope. And specifications have been developed for these bitumen stabilized materials. And what we've found with this compaction system and a standard curing system is that we get very good coefficients of variation in the materials. So that's very encouraging from those tests. And we've done more than 200 different mixed designs using the system now. And with small refinements, we're getting very reliable results. The question often arises, okay, it's not asphalt, you're not coating the bitumen, surely it's susceptible to moisture. Well, we need to evaluate that as part of the mixed design. And what one does is for another 2 of those triaxial specimens, so we tested 8 in optimal conditions, and then 2 of them we then test after conditioning in moisture for 24 hours. And what you will see is a reduction in the cohesion of that bitumen stabilized material. And that can be specified. We can limit the amount of reduction that is allowable, and that's exactly what we do. So we say you can only lose 25% maximum of the cohesion in the material. Just 4 quick examples of some of the benefits moving to the triaxial and not just using RTS testing, indirect tensile strength, as part of the evaluation of these mixes. But I must clarify, we still use it to to do the initial mix design tests, where you have a look at what sort of active filler works best with the aggregates that you are using in your bitumen stabilization, and what is a typical optimum binder content. And then that potential mix is taken forward as a composition that's evaluated, only one variable in the triaxials. So the RTS test is useful for many variables. So what we've found is with this development, we've got a ruffling device, and we compact the triaxial specimen in layers on a volume basis to get a consistent density all the way through. And that's helping us produce reliable and repeatable specimens. A second area is, and I'll show you in a minute, the shear strength of the bitumen stabilized material can be used directly in performance prediction. An RTS value has not got a very strong link with the performance of the material in the road. We've also seen that the moisture damage is providing us with reliable insights into the moisture damage of these mixes, tested with realistic accelerated testing and moisture exposure. So those limits are promising. We've also found in cases, and this is with recycling projects, where RAP has been used that's been modified, so it's not an unmodified binder, where the RTS results looked promising in terms of our specification requirements, but the red flag came up when triaxial tests were done, and it was found that some adaptations to the mix composition were needed. So just basing decisions on the RTS values in this particular case would have led to disastrous performance. Another area is how to optimize the mix. So if one's working in a hot region, what we learned is that although we do as standard these triaxial tests at 25 degrees Celsius, one can adjust that temperature if you are anticipating using the mix in a hot region. And this can link to something that was mentioned in a previous presentation, where be careful of using 100% RAP where the binder of the recovered RAP is still relatively soft. One will pick it up in this test over here, but there are solutions in blending with a 0.5 crusher dust, which is going to fit into that sand matrix of these mixes. Conceptually, how do the mix design results fit into the structural design? Well, one analyzes the pavement structure, and particularly we look at the principal stresses in the bitumen stabilized layer. There we can again rely on the Moore-Coulomb plot, where we can plot the Moore-Coulomb circle, the green one, which reflects the actual stress applied. And from the mix design, we've got our failure envelope, so we can get a deviator stress ratio, because we can calculate what would the deviator stress be, which would be the diameter of the dashed purple circle. And the ratio of those two is what we call the deviator stress ratio. And as we know, the rate of rutting that takes place in these mixes is directly proportional to the stress divided by the stress at failure, if I can put it simply like that. So that deviator stress ratio is a critical performance parameter, which we can get from analysis and from mix design. And we can therefore limit the damage. The next step we've taken, and this has come out just recently, one of our studies has been based on 25 separate road sections of 15 different regions and structures, all including either foam bitumen or emulsion as binder. And most of these areas are older than 15 years. They've been performing under traffic for 15 years. Gathered that data and then developed a mechanistic empirical design function. So this is the number of standard axle repetitions, and A, B, C, and D are just material coefficients. And we've got the 4 input parameters are the density of the material, the allowable plastic strain, which is going to limit to, for example, 10 millimeters of permanent deformation, the retained cohesion, which is a property of the moisture resistance of the material, and this deviator stress ratio. So that combination of parameters goes into the design function and helps you to accurately calculate the required thickness. We've compared it with alternative design functions that we have been using previously and found a conservative nature in some of the other design functions and also less strong links with performance in the pavement. So it's encouraging to have a more robust design system. Finally, Mr. Chairman, I'd like to get to step 4, which is the implementation and closing that loop. So this technology has been applied, and I'd like to give you one example of an area where it was cold in plant recycling, which was an extremely challenging project. It was in Sao Paulo, and I got involved with a colleague in project on the Ayrton Senna Highway, near to Sao Paulo, going in the direction of Rio de Janeiro. And as you can see, very heavily trafficked roads. Another restriction was the time available. So you've got 7 hours to do the project. This is what you're facing on this. It's a concessionaire. That's one of the areas with less barriers to change and more welcoming of innovation. The challenge was that the problem lay in the top 350 millimeters of the pavement, the highly cemented base layer which was cracked, and the holding measures and the maintenance being carried out by the concessionaire would last anywhere between 9 months and a year and a half if you're lucky, because milling off the asphalt and replacing that 100 millimeters of asphalt would just get reflective cracking. So how does one treat a pavement like this? You've got to treat the whole problem, 350 millimeters. You've got 7 hours to do it. You can't pave 350 millimeters of asphalt in 7 hours and open to traffic. So what was implemented, what our suggestion was, do a trial section, we'll see how it performs. The solution was take off the asphalt, put it into stockpile, so we've got wrap. Then take off the cemented layer, put that into a separate stockpile. If I just go one step back, if I can, whoops, no, wrong direction. So that goes into stockpile. From a previous stockpile, we do an in-plant mix and pave back 2 layers of cold mix bitumen stabilized material, 200 millimeters, paver laid, the second 130 millimeters. And then the solution from the asphalt manufacturers was a temporary 20 millimeters of surfacing, and then you can go to church and pray. Because you've got 15,000 vehicles waiting to come down on you the next morning at 5 o'clock. So we used the same design system for this project, that deviator stress ratio. The idea was that within 3 to 6 months, one would need to mill off that sacrificial layer and repave it with a 50 mil solution. And I'll explain to you exactly what happened in the end. So very briefly, to fit in with the proper implementation of this technology, one needs to process the wrap and have very good quality control with the grading. So it went through a mobile impact crusher, very low transport. This was alongside the highway, and then into an in-plant mixer, and there were 2 different mixers, and ironically, well, happily it fits in with what was said in previous presentations, and that's the bottom layer of 200 millimeters was 100% wrap, 2% foam bitumen, and a percentage of lime. The second mix above that required a bit more shear strength, required 15% of this crusher dust and the 85% wrap, just to give it some more shear strength in the upper pavement. And just a few insights into what the project looked like. So this was the slow lane, and you can see the milling off the asphalt and then the 250 millimeters of cement stabilized layer. This is already the second layer, as you can see, paver-laid 100% wrap with the foam bitumen stabilization, leaving a 20 millimeter step where the asphalt can fit in flush with the layer alongside. And that's doing the final compaction just before opening to traffic. This is what that layer looks like years later. It has now been down for more than 4 years, some places a little bit longer. This lane has now been rehabilitated, but only in one section to satisfy the concessionaire. That 20 millimeter asphalt layer was milled off and a 50 millimeter one was placed, but more than 150 lane kilometers have been constructed, and somehow that 20 millimeter asphalt is still sticking to the top of the bitumen stabilized layer. It is a bit of an extreme example. I prefer the more, let's say, calm examples of this technology, but it just shows the flexibility of being able to use cold recycling in a right way. So closing the loop means monitoring those sections over time. And this is what we're doing in updating our design systems currently. So monitoring the actual performance, and is it measuring up with the design models that it was based on. And I think this is a very important part of the closing the loop that has to happen with these new and innovative types of technologies. So, Mr. Chairman, thank you very much for your attention. And as you've seen, I think in mixed design and pavement design, there are more reliable ways of implementing this technology. So, merci beaucoup pour votre attention.
Merci beaucoup, Kim. Malheureusement, je pense que nous n'aurons pas de temps pour la question, parce que sinon les deux autres orateurs seront lésés sur leur temps. Mais les questions pourront venir après la séance. Ok, merci beaucoup, Kim. Donc j'appelle Monsieur Osamu Kamada, qui va nous faire part donc des expériences de recyclage au Japon.